buenas tardes a todos. Bienvenido al último coloquio de esta primera parte del año. Gracias Pablo por haber aportado unos cuantos coloquios en esta parte, así que gracias por eso. Siempre nos viene bien y aparte muy interesante siempre. Bueno, bien, hoy tenemos el gusto de presentar a Gustavo, Paganini Canal, ¿sí?, que es profesor asociado del Instituto de Física de la Universidad de São Paulo, ¿sí? Y él nos va a hablar sobre ciencia de fusión nuclear y plasma, actividades en ciencia de fusión nuclear y plasma en Brasil. Bien, les cuento un poco su biografía. Bueno, Gustavo es doctor por la Escuela Politécnica Federal de Lausanne en Suiza, ¿sí? Luego hizo un postdoc en General Atomics en el laboratorio de física del plasma, Princeton, ¿sí? Luego, ya en la Universidad de São Paulo, ¿sí?, fue profesor visitante y luego profesor asociado, que es el cargo que ocupa ahora, ¿sí? Y por otro lado, a nivel Brasil, digamos, es secretario ejecutivo de la Red Nacional Brasileña de Fusión, ¿sí?, coordinador del programa de física del plasma dentro de la Sociedad Brasileña de Física. Bien, y coordinador del proyecto TCABR en Brasil, que seguramente nos va a contar un poco de qué se trata. Bueno, Gustavo, muchas gracias por ser parte de estos coloquios del IB.
Let's change now to English, since my Spanish is not that good. So first let me thanks Juana, she's not here I think, no. Juana, Hugo, Pablo, Ricardo y Jorge por la invitación. And for those that doesn't know, I'm here actually in vacation with my family, and then a contact that is friend of us, Vinicius Duarte from Princeton, he told me, Gustavo, why don't you visit the people there at the Instituto Balseiro? And then I said, okay, that's going to be a great vacation then. So that's why I'm here actually. So let me start. The main idea of this presentation is to present to you guys where we could collaborate. That's the main point of the presentation. That's what I want to make it clear. So in my slides I'm going to present the different lines of research that we are carrying out in TCABR. It's the name of our tokamak. And I will stress where perhaps we could start a collaboration. And of course, I'm going to present a bigger picture of fusion in Brazil and where we are in the modernization, on the upgrade of the TCABR, and where does it fit within the bigger picture of nuclear fusion in Brazil. So just to give you some brief, very, very brief view of history of fusion in Brazil, perhaps Ricardo is going to kind of remember this age of fusion. So we started in the 80s or in the 70s actually. And then I have just one single slide about this history here, history of nuclear fusion in Brazil. It was kind of dying in Brazil, and now it's coming back out of the grave again. And then I will talk a little bit more about the national program and the upgrade of the TCABR tokamak and the different lines of research we are carrying out. So in the first part, so perhaps Ricardo kind of might remember this, but we started, not we, because I was not even born in these ages here. I was born somewhere here. But the people in the beginning of the 70s from USP, São Paulo, INPE, São José dos Campos, and Unicamp from Campinas, they started to work on fusion. So the IFUSP group were the very first ones to start a project. So they designed and built the TBR-1 tokamak. They designed it and operated the machine until 1999. At some point the INPE group designed a tokamak which was called ETA. It was a spherical tokamak. But then it was too big for the money. They had to cut it a little bit. Then it became the proto-ETA. In parallel, when the IFUSP group, that the INPE was designing a new machine, they also started to design the TBR2 machine. And then the money was too low again, too little for the bigger machine. They decided to merge the two projects, which became the TBRE machine, and then Unicamp came in at this point. They started discussions within the Ministry of Science and Technology, and again, fusion didn't win, and they had to split again, and each individual group had their individual solution. So the IFUSP group brought from Switzerland the TCABR machine. The INPE group decided to build themselves a smaller machine, which is a spherical tokamak, the ETE tokamak. And then Unicamp, they brought to Brazil the Nova tokamak from Japan. So Brazil has 3 tokamaks. A small one, brought from Japan, a relatively small one, spherical tokamak, and TCABR, which is the largest one. And we are the only country in the south hemisphere with a tokamak, and not 1 but 3, because of this, what we call this golden age. The problem is that after some time, all these people here, they started to retire, to die, to move to other areas like technological plasmas, and the number of people working in fusion reduced significantly. And that's the scenario that I got when I arrived from the US. So I spent like 10 years abroad. When I came back to Brazil, that's the scenario I saw. So I had to take a decision. So either I also move to another area, or I'm going to the grave and help this dead body to come out. So that was my work in Brazil, to resuscitate nuclear fusion. And with a lot of politics involved in this, a lot of discussions and all this magic that we have to do, it's not related to physics. So we were able to write a national program that I'm going to explain right now. This is the front page of the document. You can see here I appear as the first author of the national program. In this document, we defined the main objectives of the national program. More specifically, we had very, very clear and in short terms, the short, medium, and long-term guidelines and real actions that we have to do to implement a national program in nuclear fusion. And we based our national program on 3 pillars. The very first one is the construction of a national scale laboratory to concentrate and coordinate our efforts. So without a national lab, there is no way we can contribute significantly on nuclear fusion. It's a very expensive experiment. It's too big. Lots of people working simultaneously. So there is no way we can do this in a small lab. So we do need a national scale lab. That was the first pillar. The second one is, even if we get the money, do we have people to work in this national lab? That's a question that the ministry made to me during these conversations. Okay, Gustavo, if I give you all the money that you were asking, how many people are going to work in this laboratory? Then I had to come back to USP and rethink how I'm going to ask this question. That's why I ended up with 28 students now to rush against time to have a new generation of plasma physicists and engineers working on fusion. But we have to train the new generation on nuclear fusion. And the third pillar, which is also very important, especially for the politicians, to give money to us is to have the progressive involvement of the national private sector. Without this third pillar, it's hard to convince people that it's good to put money now in fusion. Because fusion is the energy of the future, always. But the future never comes. It seems that the future is always in the future. So how can we sell fusion now to have an immediate return? We can sell all the technology around nuclear fusion. And those are the three pillars. If you guys want to have a look in the document, we have a web link here where all the documentation is there. Of course, it's in Portuguese, but it's quite easy to translate today with AI. And in this document, the national program, we also had here the short-term, medium-term, and long-term activities. So we have 3 years, then another period of time, and then we have here this in reddish. Of course, as the time passed by, the uncertainty also raised fast. So everything starts with the construction of this Laboratório de Fusão Nuclear, which is going to take about 2.5 years. Then we are going to upgrade both machines, the ETE and TCABR, during this time. And we are going to start to design our new tokamak, a bigger one with superconductors, high temperature superconductors. After this third year, we are going to have a decision point where we are going to decide which machine, the ETE or TCABR, is going to be operated in the new laboratory, while we design and construct the new tokamak, the superconducting tokamak. And that's the second phase, where we operate one of these two machines and finish the design and construction of the superconducting machine. And then afterwards, we operate the superconductor machine until a decision point. The question is the tokamak the best route for fusion? We are going to answer this here. Perhaps accelerator is the solution, I don't know, or a linear machine. We have to ask themselves if does it make sense to put money in tokamaks. We are going to ask this in here. So that's the whole story of the national program. This is an image of the 3D virtual building that we have with the executive project. So everything is designed already, and we are just waiting for the financial resources that we might receive now in the beginning of next year, around 120 million reais in Brazilian currency, which translates to perhaps $55 million. As I said, we have 3 tokamaks. This is the very first one, the Nova UFES. It's a small one, you can see this. This is the one that came from Japan. This is the ETE that was designed and built entirely in Brazil by Gerson, Ludwig, and INPE. It's a small machine, but it's a spherical configuration. The spherical configuration has lots of advantages in terms of efficiency on how you can extract the energy once you start producing energy. And the TCABR, which is a conventional aspect ratio machine. It's more like the plasma behaves more, or the shape of the plasma is more like a donut shape. And this is the biggest one that we have in Brazil. These 3 machines, they play a role in the national program because these are the machines that we are going to use to train our new generation. And in order to train our new generation of plasma physicists and nuclear engineers, we had to pick our machine and decide what can we do with a small machine that other bigger machines cannot do. So we had to look for a little space in the apple that nobody has beaten yet. So we found a space that nobody is looking at, but it's very important. And we identified this with the collaboration of people from San Diego, from Princeton, and they helped us to design this upgrade that we could contribute significantly so that people from abroad would be interested in helping us. And they are helping us now in the modernization. We are sending students for them to supervise, to work on our machine, and that's how we are structuring our resuscitating nuclear fusion in Brazil, through the help of colleagues from other labs. And the very first thing about this upgrade is the installation of in-vessel resonant magnetic perturbation coils that are used to suppress some plasma instabilities that occur in the edge of the plasma. So let me talk a bit about this. What are these instabilities? So probably most of you have seen this solar instability. You have the sun, and suddenly you see a mass ejection of particles. So this solar ejection of mass, then these particles travel through space, arrive here at Earth, are deflected to the poles, and then we get the auroras at the poles, the lights in the sky. The same thing happens in a tokamak. When you try to increase the pressure in the plasma to make it hotter and hotter and hotter to make fusion, the pressure is too large for the magnetic field to contain the plasma. So it escapes. Like when you are cooking beans, you have this pressure cooker. Then you have a little valve at the top that like that. So like that, it's an elm in a tokamak plasma. So you have escape of pressure. And one single elm edge localized load can destroy the first wall of the machine. And here you can see this is a peak heat flux arriving on the first wall of the machine. You can see the order of magnitude is about 100 megawatts per meter squared. The most advanced material that we have today supports 10, perhaps 12 megawatts per meter square. One single elm goes to 100, so there is no way materials can survive this expel of particles. So when engineers don't come up with a solution, physicists have to come up with some scientific solution. And one of the predictions of these instabilities in a larger machine called ITER, they are going to have peak heat fluxes of the order of gigawatts. So for sure there is no way we can have a material that can survive that. So we do have to come up with a scientific solution. And the scientific solution came from Todd Evans from General Atomics in San Diego. He was my boss when I was working there. In 2006, he proposed a set of magnetic coils that you put around the plasma and you create a specific topology of field lines and kind of shape them in a certain way that you can spread that single peak of instability into something more distributed over time. And these are called the RMP coils, the resonant magnetic perturbation coils. What is the problem of this coil, of this technology, let's say? Well, let's talk about first the good thing. So here you have spikes. Each one of these spikes, you see here the envelope, but this envelope is actually composed of many spikes. Each one of these spikes here are one single elm, one explosion of the plasma surface. When you switch on these coils, you see they go away. Then when you switch off the coil, then the elms come back much more strong because they were kind of, they stopped for some time and then they got enough energy As you switch off the coil currents, they boom, give you a bigger explosion. What is the problem of these coils? The problem is that the physical models don't work to predict what's going to happen. So 3 kiloamps, is it enough to suppress ELMs? There is no physical model that can give you a quantitative prediction. Qualitatively, they work. Well, they work because they worked at the first time. When they installed and tested, they saw ELM suppression. But for bigger machines, how much current do we need? So our models don't work, and that's the space that we planned to fill up the scientific gap that nobody is looking sufficiently. And we want to stress these issues in our machine, in our upgrade, and validate in extreme scenarios, validate our physical models. So we are installing 108 RMP coils inside the vacuum vessel of the machine. Just to give you some numbers, the machine in the world that has the largest number of RMP coils has 18 coils. We are going to have 6 times more. We are going to have 108. So we are going to have, like, this is a poloidal set of coils, and we are going to have 18 systems of this one. So you have in total 108 coils inside the machine. So in this way, we can break the symmetry of the plasma in a very extreme situation to really validate the codes. And how does this fit within the vacuum vessel? It's quite challenging because the vacuum vessel is not that big, and these coils, they take much of space here. So we have to fight for space within the vacuum vessel. This is a 3D model of TCABR. This is just to give you a kind of scale. So this is about 2 meters of height. These are the graphite tiles. We are going to cover the entire inner part of the vacuum vessel with graphite. And of course, you might already anticipate that there are many technological problems here. For example, each coil we want to operate with high frequency, up to 10 kilohertz. If you put 10 kilohertz and about 1 kiloamperes in each coil, so if you have high frequency in a coil with high current, you get high voltage. So for each individual coil, we must have feed-throughs to enter 4 kilovolts, 1 kiloamp to work up to 10 kilohertz. And with these coils, we are going to be able to rotate the plasma toroidally. We can apply individual modes simultaneously to make them one mode rotating in one direction, the other mode in the other direction, with different speeds. We can do lots of magic here. And there are lots of challenges. For example, our machine are going to operate at 200 degrees Celsius for baking, for vacuum improvement. All the materials that we are using inside the coils, for example, the epoxy and the graphite, they have to be compatible with high vacuum. And each one of these 108 coils will be subject to about 6 kilonewtons, 600 kilograms of force in each coil. So we just want to make sure that all the supports are strong enough so that if one single coil breaks up inside the machine, it's going to fly out and break all the other ones. So this is a very serious issue. And we are having support from colleagues from PPPL, Alex Nagy and Rajesh Mengi. He was also my boss when I was at Princeton. Oops. This is the mechanical design of our coils in this part that we call the Z equals 0, the equatorial plane of the plasma. You can see that we have lots of screws here because of those forces. The inclined coils so that we can shake the plasma from up down. We also have some structure here. And what we call the center post or CP coils. They are made up of a single block support here. And you can see here that the forces acting on the coils, this is a simulation using the ANSYS software. It's a commercial software that does electro-thermo-mechanical simulation of the functioning of these coils. And you can see there is a brake down here. This brake is to avoid full co-current, induced currents during AC operations, high-frequency operations. And you can see how these things are deformed during a discharge. The screws, they also suffer a lot. And all these issues here, they are already solved by our engineers working within the group. We also tested how the temperature of the coils are going to raise over a day of operation, and we saw that the red curve, for example, is the temperature of the wire in the very center of the coil. Then around the wires we have the coil casing, a metal casing that houses the conductors, and then we have the bolts. So the bolts, they don't heat up much over a day of operation, but the wires, they can heat up. And the wires, they have an insulator that can support up to only 250 degrees. So we have to make sure that during a day of operation, during the last experiment of the day, the temperature in the very center conductor does not go up and destroy the electrical insulation. And after we did the design, even with the brake of the coil to avoid full co-currents, when we simulated, we saw that the magnetic field produced by the coil was strongly reduced. And then we realized actually that the current was exiting from the coil. It was going through the vacuum vessel and closing the circuit. So then we had to come back and change a little bit the design to include some ceramic insulation here to avoid the full current to close through the vacuum vessel. And we are already designing the process of construction, so there is no existing process to construct this coil. So we have to design even the process. So we are working out now within the IFUSP mechanical workshop to develop one coil winding, one way of how to wind these coils. And we also have a partner working on that, which is the FCA Brazil. It's a private company that is being funded by the project. And they are also designing this new method of winding these coils without damaging the insulator, because the wires must be under mechanical pressure. So if the pressure is too much, you just remove the insulator and then you get a short circuit, sorry. And that's a big issue. And how do you impregnate the conductors with epoxy? Because the conductors, they have to be rigid in their positions. So there must be some epoxy around. And so basically we have the coils inside and we have some space here for the epoxy. It's gonna flow down here and then go up, fill up this region, and then it goes to another reservoir in here. And then we have to make this a few times to remove the bubbles. And we have to put negative pressure with respect of atmospheric pressure to make this epoxy, liquid epoxy move. And then at the end, hopefully, we have the conductors in their position with the electrical insulator correctly positioned. And after we get the coils ready, we can install them and start using them. For example, now, if you take a plasma and perturb it with either these two coils here, for example, you can create these separatrixes here, and when these lobes, magnetic lobes, intercept the wall, you start to get some striations where the particles are deposited. During some mass ejection, like an elm, you get the particles arriving in what we call the magnetic footprints. In a real tokamak, this is an image from an infrared camera. So this is the places where the particles deposit. And we can simulate with our modules here. And we saw that, of course, they don't match. That's why our codes don't work. And we have to validate them. So we have to introduce more physics in the codes. We can do these calculations for what we call single-null plasmas or snowflake plasmas. And the structures that appear here are very different. And we can test all of this. This is a single-null configuration in our machine. So this little white-blue region around the plasma is the region where the particles are deposited during a, for example, during an elm. These are calculations of perturbations using this coil. I'm not going to get you boring with these calculations, but you can go up to n equal 9 perturbation here. So you can see that we can modify all these structures in the code for simulation. And we can also use the CP coils, and you see that the structure, it changes. For n equal 6 and n equal 9. Then we want to test the effect of these RMP fields in different plasma geometries. For example, we can have like a donut. If you cut it up down, you can see the section, the cross section of the donut. In this one, it's a circular shape. But in TCABR, we are also going to produce elongated plasmas, triangular plasmas, negative triangularity. This is a hot topic now because these configurations, they can suppress elms. So you don't need RMP coils. There is a small range of parameters that you can suppress turbulence, for example, and improve the plasma confinement. And you can also do a more square plasmas. There are theoretical works publishing now that squareness has a stronger effect on elm stabilization than triangularity, but no machine can do this. So we are going to be the very first one to test these hypotheses. And you can see here that in this case, the plasma touches the wall. These configurations that I showed up, so they are wall limited, so the plasma really touches the wall. When you detach the plasma from the wall, you get an X point, and then your confined plasma doesn't touch. This is a better configuration. You can have a double null, a double X point, and then when you bring this upper X point and put it exactly on the top of the other, you get the snowflake, which is a very nice configuration because now you increase a lot the area where the heat and particles are being distributed. So you reduce the peak heat flux. And only TCV in Switzerland can produce this configuration. And now we are going to be the next one. And the advantage here is that TCV that can produce this configuration does not have RMP coils. So we are going to be the only one to produce snowflakes and perturb the snowflake with RMP coils. And even rotating the fields. Of course, to produce these configurations, basically what you have is a current ring. So how do you keep the plasma far from the walls? How you control the plasma? So then you have to have a plasma control system that can manage 220 plus measurements and act on each one of these red coils to keep the plasma in certain shape and in a certain position. And of course, we have plenty of space to collaborate here. We are developing high power supplies and high performance too. This is the electronic topology that we are selecting. So you can see here that this is the set point. The red one is the set point, the blue one, and then the red one is exactly what the power supply is delivering. So our power supplies are being designed already, they are being constructed. They were designed in 2020. And one of the ways that we found to sell fusion to the politicians started in here, because in Brazil there is a large program now for electric trains. So we are tripling our rails in Brazil. And there is no company to supply these electric motors. These power supplies here for fusion, they are exactly the same for electric trains. So we told to the government agencies that, okay, we are going to start developing technologies that can be readily applied to another sector of the economy, which is transport. And this is very important when they see that it's going to have some return, not in 10 years or 20, but now. And we are also designing the trajectories of the power supplies, so how the voltage and current have to change in time so that you can generate the plasma shape that you want. And we have to do this for each one of the currents in the red, here in the red, and also in other coil currents here. And all these tools that we are using here, they are all being developed within the group. So we don't want to basically bring black boxes. We are developing them ourselves. We are using PhD students for that, to develop new codes, numerical codes. We are collaborating with people from software engineer, computational engineer. Since we don't have this expertise within the group, we are going to install graphite tiles to cover 95% of the inner wall. Since we desire to stabilize elms, we have to make sure that we get elms in the first place. So we have to be sure that the plasma is hot enough, and the plasma loses heat through radiation, and the power that plasma loses goes like the Z squared, atomic number squared. So if you have iron in the vacuum vessel, it's 26 squared. If you have carbon, it's just 6 squared. So the plasma stays hotter with a carbon wall. Another important thing is we are upgrading this small tokamak to test something new. Imagine a transformer, for example. If you have a normal transformer, transformers, they work under AC current, but there is a mechanism in the plasma that you can apply DC voltage and you can get DC current in a transformer. So this is called helicity injection, and you can do this by applying a filament or plasma filament that goes up like this. Here we are going to install 2 plasma torches in the bottom and create 2 helix of plasma going up, and you have strong currents circulating. When you have the current in 2 conductors, when you have current in the same direction, the currents attract. So if these 2 if this distance is a little bit smaller than the other ones, these two filaments, they will shortcut. And then you are going to get a plasma ring, and the other current goes like this. So you end up with a plasma ring, a current ring. And then if you keep shortcutting these things, you populate a plasma ring or a plasma with electric current rings. And you can sustain a plasma with inductive current applying DC voltage in these plasma torques. That's a way to sustain the currents that are about 150 kiloamps. Let's say 10 lightning bolts at the same time. And at the end, we are developing new diagnostics for our machine. We already have Mirnov, Rogolsky, flux loops, diamagnetic loops. Because of the 3D fields, we are going to install pseudo coils. We also plan to install a whole zoo of electrostatic probes, the reciprocating, wall-mounted Langmuir probes, ball pen probes, Mach probes. In some tiles, graphite tiles, we are going to install tile current shunts to measure thermoelectric currents. We have Thomson scattering, spectroscopy, H-alpha and D-alpha detectors, and we are going to have visible and IR cameras. We have microwave diagnostics, X-ray and UV diagnostics. We are starting now a collaboration with Lausanne in Switzerland to start some new way of diagnosing the soft X-ray emission for MHD detection. And just a summary. So we started a national program for nuclear fusion, and we have the 3 pillars. That's the main point of this presentation, just to present you the 3 pillars: the construction of a national scale laboratory, trading of human resources in new fusion technologies, and have the private sector to get involved. I didn't mention all the different lines, let's say, of commercial lines of technologies around the reactor that can become a product right now. But we have a set of 7 different lines, and we attracted the private sector with those strategies. And in TCABR, we are making an upgrade to validate physical models that can work as an engineer tool for future fusion reactors. So we plan to perturb the plasma with these extreme RMP fields, study the plasma response in a variety of plasma shapes, and independent power supplies, they will allow to apply RMP fields with different mode numbers, rotating simultaneously with different velocities. And I didn't mention, but all these 108 coils, each one must be powered independently. And these coils, these power supplies, they also have application. For example, in the area of distributed energy generation, for example. They can be used to convert from DC to AC in solar panels, in wind farms, and there are lots of applications here. And I'll finish here, and thank you guys for the invitation again. And we are very open for collaboration. We have lots of becas in our home institute for students, if you guys want to send students there. Of course, if I tell my students that they can come and spend like 6 months here, they will love it. But the point is, we are very open for collaborations here. Thank you.
Muchas gracias, Gustavo. Bueno, abrimos a preguntas.
Gustavo, can you tell us a bit more about what is the interest of the private sector and what are the technologies that they're interested in?
For example, the power supplies for controlling plasma shape and position, they can be used for electric trains. We have no companies in Brazil with know-how on how to build these power supplies. So everything is brought from other countries. Now we have a company that can do this nationally, and it's a market of something like $30 billion. And we now have a company that can profit from this market. The same thing is the power supply for the 108 coils. This one is also a plan to use it in the new energy market. We also have, for example, soft X-ray detectors that make a tomography of the plasma section. If we just pick this cross section, turn it in the horizontal plane, and if you use it, for example, to diagnose some pillars of a bridge, you don't need to make a hole in the pillar now to see what's going on inside. You can diagnose the pillar without destroying it. And this is an example, for example, in Brazil, for example. Let's say if Banco do Brasil wants to buy a whole building, it just wants to make sure that the building is in good condition. So it can scan all the pillars of the building and check if the metals are oxidated or not, and things like this. You can use it in lots of things. The graphite tiles, all the material technology can be used in siderurgical applications for, I don't know how to translate, for autofornos, for melting iron, these refractory tiles. Space research also benefits from this material research. For example, when a spatial vehicle enters back in the atmosphere, it gets something like 3 megawatts per meter square of heat when it comes back during the re-entry. 3 megawatts per meter square. We are getting 100. So our materials, they can handle, they can work in a very extreme environment. So if our materials work within a tokamak, for sure they are going to work in space for satellites or for spaceships to go from Earth to Moon, or I don't know, to come back. There are plenty of things around a nuclear reactor that can be used right now. That's the message that we can sell to, let's say, politicians, so that they can realize how important it is to put money in fusion right now. If that was not a reality, the first world countries, they wouldn't put money now, but they are putting money, private money. So they already realize the benefits. The fusion market, we are getting close to the $6 billion coming only from private funding agencies. So the public funding is already like 20% only. So the private money is much, much bigger than the public money now in the fusion market.
¿Las preguntas?
Oh yes. Yeah, the very first step is to start building the lab and finish the lab. And during this period of building the national lab, we are going to start the design of the superconductors, the coils, and everything. But before we get the money for the lab, I would say we should not start looking into these more advanced things. Let's first do we call it in Portuguese the BAB, ABC, let's say. Let's do the ABC first, and then It's Arabico, yeah. Actually, the name of the... Actually, it's not patent. I was very surprised. For example, I got in Brazil the owner of the company in Italy that made, out of the 18 toroidal field coils, he made 9. So half of them was made by this company in Italy. And then he came to Brazil, we were talking, and then at some point he told me, Gustavo, when you guys start to build, to design and build your coils, come to me and we can make an agreement. I get money from the European side, you can get money from your national Ministry of Science and Technology, and you can send your engineers to here, to Italy, and I can send my engineers to your place. And then I got, but why would you do that? Why would you teach my engineers how to do it? And then he said, well, because it's not patent. And then he said, but why not? And then he tried to explain why. At some point, basically, the main point I got was, this is so complex that even if you guys manage to get a certain age of maturity, we went already beyond. So basically, they are not afraid of us reproducing that. And actually, they are going to get money out of this. Because, for example, this company can get money from the European Union. So he is going to get money. He's going to make money, the company. So at some point, it all becomes a market. For them, it's actually good that we start looking into this. One thing, perhaps we are going to have a longer time to develop is actually the process of depositing the different layers of superconductors. This might take 6 or 7 years of research. But in the meantime, oh, that's a good point. In the meantime, how did we get the private money to start the superconductor part? Nobody in the private sector would put money in superconductor nows for fusion because they don't have fusion reactors to sell the coils right now. So I had to come up with a solution. So which kind of application I have right now of superconductivity that can give money right now? And then I saw that we can make energy storage systems for solar panels, for wind farms. The problem of these people is the following. Imagine you have a solar panel and the guy has a contract with the government of 10 megawatts of power. He has a farm that is producing up to 15. But if he produces less than 5, he gets a charge from the government, from the National Agency of Electrical Energy. So he's producing 10. He can go up to 15. If he goes below 5, he's charged. And then he must go to the energy market, buy energy to honor the contract. Sometimes the market is selling energy at some price that for him is better to get the charge from the government. If we can develop an energy storage system and plug it at the output of their power plants, little power plants, they can stabilize it. They can produce more, and then they can storage so that they can stabilize it when there is no wind or sun. So these systems, they work in a way like a capacitor. So a capacitor, you can store, let's say, voltage. If you have a shortcut inductor, you're going to store current. So in a capacitor, you store the energy in the electric field. In an inductor, the energy is in the magnetic field. So if you shortcut a coil, a superconducting coil, and if you pump magnetic flux to this shortcut coil, you end up with a lot of current trapped, and it's going to be there forever. It does not dissipate. So you can even transport electric energy without cables now. It's a whole sector of economy. Nobody can sell energy like batteries. So people now, they have these lithium batteries. But lithium batteries, they can last for perhaps 8 years, maximum 10 years. After that, the lithium battery is gone. In these superconducting materials, they can survive very, very longer, because you're storing the energy in something that is ethereal, like in a field, like in a magnet. What is around? So there is energy around. So there is no material to deteriorate that. And we are now starting a contract where we are promising to deliver a container for 10 megawatt hour of energy storage with an output power maximum 10 megawatt. And after 5 years, we hope we are going to succeed. And this is going to be the market that this company will attack. During this time, all these engineers working in this company, they will get the know-how on how to build fusion coil. So when the national program has walked already a few years, our company is already ready to produce what we need. So we are bringing everything together. The inertia is much larger, of course, but we have to bring everything together. We cannot leave something behind. Everything must be synchronized. Yeah.
Okay. Bueno, una pregunta más. Bueno, agradecemos nuevamente a Gustavo.
Okay. Gracias.
Bueno, cerramos entonces los coloquios para este primer semestre. Los esperamos para a partir de agosto. Como siempre son bienvenidas propuestas. Así que cualquier cosa me escriben a mí o a Pablo Pablo Costanzo, y bueno, ahí vamos haciendo negocios, digamos. Gracias, gente. Nos vemos.